Okay, let's get started. It's 9:33 here in California. Good morning. My name is John Min, and Kat, you should wave. So thank you for Imperas and Andy's webinar on what the custom extensions are. This is planned to be a series of webinars that go into more depth as we go. Of course, feel free to contact us. We have contact information at the end for more in-depth discussions. So quick introduction. My name is John Min. I'm the Director of Solution Engineering at Andes. And I'm joined today by Kat, who is the Senior Account Manager at Imperas. So we are a great match company. Andes creates CPU IP cores, and Imperas supports us in using models of our cores to do system level simulation and optimize your SoC designs. So to go in, here is the word from my sponsor, Andes Technology. Andes is a pure play CPU IP vendor. We are 18 years old, so we were a CPU vendor even before RISC-V came along, and we are a RISC-V founding member. We're very active in both open source and RISC-V community. Our founders have over 100 years experience in Silicon Valley. Currently, company is 300 people. We have over 250 paid licensees. We're a profitable public company. We recorded more than 10 billion chips, SoCs shipped with our IP. Our engineering center is mainly based in Asia, Taiwan, and in the little country called Canada in Vancouver. So how did the evolution of CPU IP from Andes come about? 18 years ago, we introduced first Andes Star architecture. That's the name of our architecture, version 1. And over the years, we innovated until about late 2010s. We go into a version 3, and RISC-V, Andes was looking for 64-bit architecture. RISC-V came around about that time, and we thought it was a good jump to go to more industry standard architectures. And we adopted RISC-V. Official name for our architecture is Andes Star version 5. So what that is it's a RISC-V architecture. We call it baseline, RISC-V architecture with Andes specific extensions. And that is what the RISC-V is good for. You could extend it to what you need. We have standard extensions like Codense, StackSafe, and PowerBreak, which help overall compute experience. But what we will talk about today is what's in the purple box, custom extensions, where you can add custom features to the core to make a true accelerator, true DSP, or other applications. So here are some examples of custom extensions. What are they? Well, everyone thinks about custom instructions that accelerate algorithms. The benefit of custom instruction is multifold. You could accelerate algorithms, and you could also reduce code size so that most used instructions could be mapped to a 16-bit opcode or other opcodes, reduce code size, and that could reduce instruction fetch. Imagine if you have a loop, you replace it with a custom instruction, you no longer have to fetch and decode all those instructions. Along with that, to work with custom instructions, I could create custom memories. We call those ACR, Andes custom registers, or Andes custom memories, depending on how you want to architect those. Benefit of this is it reduces data loads and store. Again, going back to those loops, the data could be kept in the registers or memories. And if you're working with AI, coefficients be kept in the custom memories for operation. So you increase the data bandwidth available to other instructions, reduce the load and store bandwidth. Lastly, we could create custom ports. One of the issues with a CPU processor is all the loads and stores go through the caches and the main buses. Well, sometimes you might not want to, especially applications like AI, where you have a lot of data moving back and forth. Create a custom port to generate a tight integration with external accelerators that could guarantee bandwidth and latency. So CPU, some of the bandwidth and latency is not guaranteed because main bus is shared with lots of other devices. You could create a dedicated custom port to your AI accelerator or GPU. So let's see how we work with these things. You customize the CPU, and this is what it will look like, your SoC. On the left-hand side, you have CPU core with the ACE engine, with the custom registers, custom memories, and custom instructions. And then you have this port called ACP. You could create dedicated buses or data ports to talk to co-processor or even other processors. Imagine two processors talking without latency and coherency issues. And then you could create both data channels and command channels, or create a von Neumann architecture as well. It is very flexible to control. And then imagine, maybe I have a custom sensor DSP that's 107 bits long. I could create my data bus to match my data width. So it's a very flexible system. So let's talk about some of the benefits you'll get. So obvious speed up is you could create a custom instruction, one instruction to accelerate a loop or a specific function. Imagine one matrix operation instruction that could do 32 by 32 matrix calculations. So you could create those. So you benefit speed up, you could get 40, 50, 100 times acceleration. But side benefit is we talked about reducing smaller code size, and then bigger benefit for especially smaller systems is reducing energy. So just fetching, decode, and executing instructions and write back takes a lot of power in the CPU. I could replace, let's say, a loop that goes to 1,000 times, 4 instructions 1,000 times. That's 4,000 instruction fetches and decode and execute. I could replace with one instruction, reduces a lot of power, so you save execution time and code size and bus bandwidth transfers. So here's some of the algorithms as an example what you could achieve. Let's talk about a FIR filter. FIR filters are used everywhere. We could accelerate it about 20 times relatively easily, but that 20 times acceleration leads to about 30x power efficiency doing filtering. And if we get a little more complex, CRC32 calculations, we could have over 150x acceleration, saving over 200x power for that algorithm. Triple DES and triple DES is in 300x acceleration. So overall, you're trying to achieve a specific fine-grained acceleration. So anywhere between 10 was easy to do, over 200, 300x acceleration. Some algorithms are a little better for that than not. But this includes instruction, local memories, and for this example, dedicated ports aren't used, but they can be used. So how do you develop it? Well, in the software architecture phase, you write your easiest way to do it is write your code in pure RISC-V instruction set. Once that's done, functionality verified, you profile it to identify time-critical sections, or I used to use the word subroutines, time-critical subroutines where you're spending a lot of time. And then look at that routines, define instructions to accelerate that subroutine. Has cycle met or not? Well, usually if you're like me, first time, some of the instructions don't work. It has some side effects. So it's important to have a good simulator to estimate cycles and performance. Once cycle is met, you go to RTL phase and implement your RTL. Again, evaluate PPA. Did it give me enough benefit for performance, cycles, or power, right? You wouldn't create instructions that made your performance worse, either in execution cycles, or power area. So it's an iterative routine. It's a standard time-tested engineering development method. And by separating my golden model, my pure RISC-V code, versus accelerated cycles simulator, and then the RTL, we get some extra benefits, like we have a tool called Copilot that can automate all this process. But on the left, we have custom instructions, standard RISC-V, middle custom instructions simulating, and then the RTL. By having these three steps, the benefit is we get an automatic cross-checking environment that custom instructions. Did it give me acceleration over previous unaccelerated code? Is the result the same? Are there any side effects that I should know? And then you could cross-check results from the three different methodologies to make sure you got the performance and features you needed. So Copilot is our software development tool to simulate and create custom extensions. Now, here is what we can do. Is my gray box includes what my simulators could do, which is simulate the core, simulate custom instructions and custom memories. That's what it's designed to do. Now, the one thing it can't do is simulate and emulate entire system to develop system level software. My simulator is single core. Maybe in your system you have 4 or 5 cores, or maybe 10, 100 cores. And then some AI or GPU accelerators, system level memory. So you could create instructions, see the acceleration. Now, if you need system level impact, that's why we work with Imperas, who could deliver that performance simulator. So at this point, I'll turn the presentation over to Kat. She'll present her slides and tell you how you could do it from the system level.
Thank you, John. Let me share my deck. Setting things up. Hi, everyone. I'm Kat Shi, Senior Account Manager with Imperas. I'm very excited to be here to share with you our contributions to RISC-V and custom extensions. So before I dive in, a quick introduction to Imperas. We were founded over 15 years ago with the principal belief that nobody tapes out the chip without simulation. Therefore, no one really should develop embedded software without simulation. So today we are a world leader in simulators, tools, and debuggers and models, especially processor models. We help embedded systems developers get their software running and the hardware engineers get their designs correct. We are based in UK. Our team has extensive experience in EDA, processors, and embedded. In addition to Imperas.com, we also run OVPworld.org. That's where you can find a lot of technical resources and download free trials. So thank you, John, for teeing this up for me. Picking up from where he left off, John talked about Andy simulator. Andy has a near cycle accurate simulator, which is great for simulating single core or just a few cores. Imperas is terrific at the whole system. So here is the diagram where John said there's the rest of the SoC, and that's where Imperas can come in. Now, to put things in perspective, the gray box that John showed can be one of many, many cores on a complex virtual platform simulated by Imperas. Here on the right-hand side, I show a large control processor that's driving, say, 4 million cores. So adding the peripherals and bus and memory to what I just showed shows a much more realistic, a bit more detailed virtual platform. So on this light blue virtual platform, we illustrate it with Andy's N25 ports that is connected to peripherals, to memory, and it boots up free RTOS. On the bottom of this SoC, there is a Andy's application processor AX45MP that boots to SMP Linux. In Imperas, we call a virtual platform that already has software running and extended platform kits. And it's a terrific way to share this kind of already built, ready to go platform with your internal and external team, such as your partner or your customer for early software development. Software engineers need powerful tools. So in addition to simulators, we also provide a set of professional high-end tools. So on this diagram here, I show the virtual platform in blue box. It could be a simple, say 4-core platform that I just showed, or as complex as a whole board or multiple boards. There's no physical limit. The virtual platform sits on top of API that connects to the tools. It runs application software and operating system, and it's driven by test bench. We differentiate by our processor models. For RISC-V, we support full RISC-V ISA, and we have designed a very elegant way to add custom instructions. Our simulator is very fast. Typically 200 to 500 or more millions of instructions per second. That makes it realistic to run actual workload. We have top-notch tool, multi-core tool. The first one is multi-processor debugger. It's a platform-centric tool. For example, you can co-debug peripheral with its driver. The second set is VAP, verification analysis profiling tool. It has dozens of tracing capabilities, such as trace on register change, instruction tracing, line tracing, and so on. It's non-intrusive. And so it makes it very easy for the engineer to gain insights into the system behavior of the platform. What do the customers use Imperas for? Well, I presume everyone here is already an Andy's customer or about to become one. Or maybe if you're on the verge of thinking of transitioning into the world of RISC-V, we can help you with some of the dimensions of a feasibility study. For example, one of the considerations would be, do I need to change my tool? Or how much do I need to change it? As an example, a recent trend is hybrid emulation for SoC verification. With Andy's and us, we will drop the Andy's models right in to work with your favorite emulator. Another consideration could be how much software libraries can I carry over to RISC-V. With a Imperas ISS instruction set simulator, you can easily start running some simple program and get some ideas. I'll talk about the rest of the use cases in my following slides. Architecture exploration. The key to good architecture exploration is to be able to find and run good workload and realistic real-life application. I'll take AI SoC as an example. So today, the AI SoC starts in the cloud. The models are trained in the cloud with real-world data sets, right? So lots of runs happen on the cloud. Now you have trained the model. The next step is, how do you optimize it with hardware? A virtual platform is an excellent vehicle for that, especially in Paris, because we are so fast, and you will be able to run large data sets on a virtual platform and get insights into where the optimization opportunities are. For example, on an AI SoC, customers have used us to answer the configurations of how to configure, for example, at each processor element level. How many cores there should be, how big the control processor should be, should there be accelerator within the PE? Or at the whole chip level, scalar versus vector versus adding custom extensions and so on and so forth. So we're great for even early on, before you want to start, or before you're ready to start the RTL design. Because Andes and Imperas are both good fits for automotive, I'm using automotive use case to illustrate early software development. On the lower right block, you see I have two virtual ECUs. Each ECU has two Andes cores. These are automotive ready Andes cores, N25F SE. And they are connected through a pseudo canvas, which I'll talk about in a bit. The goal of the simulation is to accelerate the bring up of RTOS and AUTOSAR RTE. It can run SMP RTOS and test AUTOSAR RTE communications layer, and that's our simulation goal. Now, because I mentioned that the goal is to test the communications layer, we don't need to model the entire canvas. In this picture, you can see that the communications is just run over the serial link. So with the virtual platform, you can really abstract the model according to your simulation goal. The virtual platform can be part of your regression test suite because compared to hardware, it's much more controllable, deterministic, and in safety critical systems such as automotive, fault injection is important, and it's easy to do in a virtual platform. So putting these together, this is what the testing would look like. Test stimuli would be pumping in from the virtual ECU1 on this side, and then the test extracted on the other ECU, and the checking is done on that side. All right, I'll talk about some high-level virtual platform use case. I'm going to talk about the integration to Andes ACE now. So dropping down from the software level down back to hardware, let me introduce the Andes processor that Imperas has built. We develop and maintains all Andes processor family models. So that's represented by my darker block, purple block, right on the left-hand side. And on the right-hand side, the orange block is the user extension. We support all Andes ACE acceleration features. And these models run on top of the Imperas simulator.
My apologies. I don't know why.
I like to borrow from John's slide again. This is what he talked about when he went over ACE development flow.
So that's where I feel like it's really not.
If you have application software for the platform level, Imperas would be a great tool to start running with that and do your architecture analysis to identify the time critical code. Looking at that flow from a slightly different diagram, the blue box flow here is the Imperas side, and the green ones are Andes. So drilling in a little bit further, the application architecture exploration starts with running a C program on Imperas, iteratively finding and optimizing your custom instructions. And once you're ready, you can take it to the Andes side and use ACE to enter the custom instructions, do cycle accurate analysis, and so on and so forth. And on the blue side, you can now add your ready-to-go custom instructions into the virtual platform. Now you have your customized processor model. And the software team can start early on with the software development, debug, analysis, and test. And these two can go on in parallel, but that cuts down more cycles. Over the past few months up to a year, we have collaborated with Andes to automate the Andes ACE to Imperas processor model flow. This is also from John's slide. So this is the Andes environment with ACE and Copilot tool. After Copilot generates the RTL, it also generates an executable. This executable can now be imported to Imperas environment, and we automated this flow to generate the custom instructions. So here you go. Now your secret sauce is part of your model. To summarize the benefits of this automated flow, it reduces developer workload. So developer doesn't need to learn how to add custom extensions. It's correct by construction right from Copilot. The ACE code can be kept proprietary. The final Imperas model provides virtual platform and tools for software development. The tools that I just mentioned earlier, the MPD, BAP, they all just work automatically with the custom extensions. And Imperas models are compatible with major EDA environments. Okay, wrapping up, I'll talk about Andes and Imperas partnership. One of our big customers, I want to share their example using Andes NX27B. This customer's SoC has more than 150 cores. It uses a mix of Andes with scalar and vector processors. The processors are used for AI ML running OS and different housekeeping functions, power management, communications, and so on and so forth. The platform simulation runs at over 500 millions of instructions per second. The engineers can choose to run the entire platform or subsets of it. It runs production binaries. And the key goal for this platform is for software development, optimization, and test. The software was up and running in Imperas environment 1 year before RTL taped out. And once the first silicon came back, the software only took a few days to run on the first silicon. We support all the Andes V5 cores, and our reference model can be integrated with most industry standard software IDEs and debuggers. We also support advanced features such as codance and ACE flow integration. In closing, to summarize, Andes and Imperas combined solution offers SoC developers with early architecture exploration and automated integrated design flow for ACE, early software development before any hardware is available. The extendable platform kits can be a virtual development board for your customer and partner for early software development, or even just to show a snazzy demo. Help optimize designs and accelerate schedules. And Andes has certified Imperas models and simulator as a reference for Andes RISC-V cores. That concludes my presentation portion. Thank you very much. Here I show my email. Feel free to ask me questions and give me comments. And LVP World is where you can go download models and look at our open source course. For Andes open source models, and go to this link. All right, I am going to hand it back to Jonah to run our Q&A part. Thank you, everyone.
Hello, everyone. Thank you for joining us. We didn't have any questions come in through chat or the Q&A, but we did have questions that arose during the registration process. So I will go through a handful of these to make sure that we've gotten everything covered. First one is, do custom instructions need to be open source?
Yeah, so idea of custom instructions is you create instructions for yourself, and you do not have to open source it at all. You could keep it secret. That's your secret sauce. If anybody disassembles your code, all they'll see is opcode mark custom instruction 1, 2, 3, 4, whatever, and then the source operand. So it'll be they will have to work at a little bit to figure out what it's doing. We've had customers create custom instructions to lock out the binary from running on other RISC-V processors. So there's some interesting things you could do with custom instructions, but they do not have to be open source.
Let me answer
and-
that from the Imperas side. The Imperas models are available under Apache 2.0 license, which means that you can take it, change it, and without having to publish it. So custom instructions do not need to be open source. In fact, part of the reason that we automated the flow with Andes is that we have customers that wants to keep them secret from the vendors as well. So that's why we automated it.
Okay. Next question, how are custom instructions supported in the software tool chain?
So there's two ways to go about doing this. The Copilot will generate intrinsics that you could use as, it would be like calling a subroutine, call it intrinsic. Changing the compiler is a big work, so especially verification. So Copilot is optimizing and making using custom instructions easy by generating intrinsics that you could call like a subroutine.
And the way that we designed how our extensions work is that it will work automatically with our tools. So it works automatically with Imperas multiprocessor debugger and verification application profiling tools.
How about next question, can custom instructions be used for an application running on RTOS?
Jonah, can you repeat that for me?
Can custom instructions be used for an application running on an RTOS?
Sure. Custom instruction could be used anywhere. In fact, it's been used to accelerate RTOSes as well for context switching.
Okay,
So
next.
the easiest way to understand where it can be used, think of as custom instructions as replacing subroutines or function calls. You create, in fact, you're creating new function call. In that, if you think of it in that concept, you can create custom instructions.
Yeah.
All right. Why is the RISC-V custom instructions different from other cores that have offered this in the past, like MIPS and Tensilica nodes?
Yeah, so there have been two kinds of custom extensions, right? Custom instructions are created by MIPS and even ARM, I think, had that mechanism. You could create instructions, and I think Synopsys ARC does it as well. You create instructions that accelerate performance. Something that's different for Andes is you could create local memories, local states, and acceleration ports. So it's much more than just custom instructions. Tensilica actually, I believe, offers something similar to Andes in that they offer custom instructions, custom memories, and custom ports. So the ability we offer is all these capability for custom extensions on top of standard RISC-V instruction set.
All right. Next question. How do you handle ongoing maintenance and ecosystem conflicts?
Well, so there are really no conflicts with custom extensions, as long as you keep it custom for you. For our customers and the Copilot and our software tools work together, compilers, to make sure that any instruction generated using Copilot is supported by our software compiler and debugger. And we push those up into the header tree. So we keep it working well. So sometimes it needs compiler extensions with specific intrinsics or data types. We make sure that the Copilot, if instruction is generatable by Copilot, it is supported by software. Okay. There's a question on the Q&A. Can you please share what kind of custom extensions Andes have on top of latest RISC-V core? So basically, we have standard extensions, right? That's different than RISC-V, or on top of RISC-V is we have a code dense reduced code size. We have a stack safe to protect stack overflow, underflow bugs issues. We have a power break for power management and software controlled frequency scaling of the pipeline. So those are called standard extensions. Custom instructions, whatever you could imagine and create. We have some examples, just you saw DES, triple DES, some of the algorithmic examples to get you started or doing evaluation. Can Imperas integrate support FPGA accelerator? I think they do. So that one's for Kat. This is Q&A.
Yes, yeah, I'm just
Yeah.
looking at it now. Thank you. Yes, we do. So please contact me. I see this anonymous attendee. That's something that is out of scope of this discussion, but do contact me and we can go into more details on that. We have designed our tools to be able to integrate to a lot of different other tools. And profiling results as well. I'm not ready to show a profiling results on this call, but we can definitely talk about that offline.
Okay, I have one more that for Kat. I'm building an SoC that needs environment input. We need audio to test the audio decoder, for example. How do you direct the audio to the virtual platform?
Oh, okay, that's a terrific question. We have a capability we call semi-hosting that I didn't get to mention on my slide, but what it is that we leverage the host machine's resources. So the simulator will be running on some big x86 server type. And for example, for an audio input, we can leverage the host machine input to get the audio file, and that would become stimulus to our simulator.
Okay, there's another question from an anonymous attendee. Can you share information if there's a matrix instruction extension on the way? There's two ways. RISC-V is always evolving, so there are always instructions being proposed and the community is debating on. There's been a bitwise operation extension that's recently approved. There's a vector instruction set that's been approved. There's a DSP instruction set that is going through approval. And additionally, you can create custom matrix instructions. So we have an inner dot multiply custom instruction example. So there are many examples. There's some open source projects I've been following for matrix calculations, where somebody was doing 128 by 128 square matrix, and they were able to achieve over 200x acceleration with custom instructions using RISC-V. So there are a lot of examples out there, and that's one of the reasons why we adopted RISC-V as a base architecture for community reuse of instructions. And if you create some instructions, and if you're kind enough to publish it, then you could help the community as well, but that's not required.
All right, so one more question. from Sissy.
Jonah, I want to comment on the custom extension part. I just saw it.
Go
The
ahead,
question
go
is, could you please share what kind of custom extensions Andy's have top of latest RISC-V for? So from the Imperas side, we see that almost every customer do custom extensions. That's the fun of and the main reason, one of the main reasons for using RISC-V. Right? The ones that we know of in the groups of memory access and security, and the more advanced extensions would be also making extensions to the core level interrupt controller, the click. So that's what we have seen.
All right, question on Q&A. Is it possible to do hardware software co-design on an FPGA with Imperas tools?
Yes, the answer is yes. I think I answered it. So the answer is yes. And that's something that we have done with customers. I'll take that offline with the person asking the question. But just to summarize, we interface to emulators, pipeline simulators, Verilog simulators. So definitely FPGA as well.
All right. Any more comments from the presenters or any other questions they'd like to answer? John, Kat?
Just to let everybody know, I think Jonah is supposed to say this, but every attendee will get a link to the video webinar.
Yes, for sure.
And we are also, as John mentioned very early on, we are looking for input to structure this into an ongoing series to answer real life topics and questions that our users have. So please give us input.
Yeah, and a lot of the tools we mentioned, like the Copilot or the Imperas tools, will become webinar by itself. So stay tuned to this channel.
All right. Well, thank you for joining us, and we'll be sending out notifications of our future webinars, and please be sure to join us at that time.
Thank you.
Thank you.